Hello everyone, welcome. We have done so far in this week is we tried to understand the basic philosophy in displacement based methods. Now onwards, the similar philosophy. Now we have different methods in a way that how that concept is being translated into methods in a different way. The first methods that we discuss is slope deflection methods. What we do today is we'll see what is the method itself, and then in the subsequent lectures we will see the application of this method in various indeterminate structures. Okay. Now let us try to understand the method through the same example that I used to demonstrate the concept of displacement method as a whole. Now this is a continuous beam which is subjected to some external load. This is an indeterminate structure and degree of indeterminacy, static indeterminacy is 4, right. Now suppose now consider only span CD. This beam undergoes a deformation in a different way depending on the external load, but for some external load, suppose the segment CD they undergoes deformation like this. Okay. So the point C goes to C dash and point D goes to D dash. We'll demonstrate the concept only through segment CD, and the final equation what we have, the same equation can be applied to all these segments separately and then combine them to get the final expression. Okay. So the C dash D dash is essentially the deflected shape of a CD. Okay. Now there are three things can happen. Okay. Suppose if the point C goes to C dash, if you draw a slope at C dash and this angle is theta C, so the rotation at C is equal to theta C, and similarly if we draw a slope at D dash and the rotation at D is equal to theta D. So theta C and theta D at the joint rotation at C and D respectively. Okay, in addition to joint rotation, we will also consider the support settlement of support C and settlement of support D. Suppose the settlement of support C is delta C and settlement of support D is delta B. So if we concentrate only on segment CD, there are 4 things can happen. One is the rotation at C and rotation at D, and then settlement at C and settlement of D. So we have now similarly if we take segment BC or segment D or any other segments, similar 4 things can happen: the rotations at the joints and the settlement of the joints. Okay. Now if you remember the concept, if you remember the last class when we discussed the concept behind displacement based method, what we did is, since the displacements are unknown here, so in the primary structure we need to remove those degrees of freedom, right. We need to make a structure we need to make a structure kinematically admissible, kinematically determinate. Okay, each segment of this structure. Now when you do that, the first step we get the primary structure which is a fixed, which is all the joints which are roller supports here, those joints becomes fixed joints. Okay. Then we separated, then we took each segment separately. Okay. Now similarly, so to get the primary structure we constrained the degrees of freedom at C and degrees of freedom at D. So the primary structure become this, isn't it, which is a fixed beam subjected to externally applied load. So this beam is CD. Now because of this loading, the moments generated at the fixed end is this. Now please look at the sign I am using for these moments. The sign what we have been using will still continue with that. When we draw the bending moment and shear force diagram, we see whether the moment is sagging moment or hogging moment, but when we do the algebraic calculations, your clockwise moment is positive. Okay. Now So that's why I took here the moments are shown in a clockwise direction, because at the end when we do the algebraic calculation, we don't need to see whether the moment is sagging moment and hogging moment. Direct straight away we can add these moments. Okay. Now this is the fixed end moments generated at C and D. So MF CD is the fixed end moments at C in span CD, and MF DC is equal to the fixed end moment at D in span DC or CD. Okay, so this is fixed end moments. Okay, now so this fixed end moments is calculated due to the external load on the primary structure. Now this segment CD now undergoes rotation and joint settlement, displacement. Because of this rotation at the joints and settlement at the joints, it will induce some moment in the structure. And suppose these moments are M dash CD and M dash DC. So M dash CD is equal to the moment due to theta C, theta D, delta C and delta B, and similarly M dash DC is equal to moment at D in segment CD due to the joint rotation at C and D and support settlement at C and D. Okay. Now, so this is the moment due to rotation and settlement of joints. Okay. Now, then what we discussed. Now this is a primary. Now these two are primary structure. This is the primary structure subjected to the external loading, and these are the corresponding moments at the ends, and this is again the primary structure, and the corresponding constraints are removed. Okay. Corresponding degrees of freedoms are removed, and then the structure undergoes some rotation and support settlement. These are the corresponding associated moments. Now total moment at C and D will be this plus this, right. So if we draw the free body diagram of member CD, forget about this thing, just the free body diagram of member CD, there will be shear force and the moments. Okay. Now again recall when we actually in previous lecture, when we use free body diagram, always we showed the moment in the direction whether it is sagging and hogging. We will still continue the same convention while drawing the bending moment diagram. Here the bending moments are shown in a clockwise direction, because rest in the next in all the procedures to follow, we'll do many algebraic calculations, and it will help us to be consistent. Okay. Now so superposition says, the linear superposition says that if this is the total moment at C and D, then this should be equal to this plus this. So primary structure subjected to response of the primary structure subjected to the external load plus the response of the primary structures with corresponding degrees of freedom constraint is equal to the total response of segment CD. And this is true not only for CD, this is true for all the segments, right. Now so we have two parts, one is the fixed end moments and another is the moments due to joint rotation and the settlement. Okay, great. Now if we can find out these two values, the fixed end moments and these values, then we can find out what is the corresponding moments in the actual structure. Now rest of the things what we will see is the basic method is how to find out these values. Okay. Great. Let us see the first fixed end moment. If you recall, in the last class we discussed how to find out fixed end moment. Fixed end moments essentially is nothing new. It is a fixed beam which is subjected to some loading, and what would be the corresponding bending moment at the fixed end, that is the fixed end moments. Now we demonstrate. So this is essentially, if you solve this statically, this is statically indeterminate structure of degree 3. If you can use any force based method to solve statically indeterminate structure to get the fixed end moments. Okay. if you take any analysis book, these are the for some typical loading cases, the friction moments are tabulated. So you can directly use those values given in the table, but before you do that, at least once in the entire course, you find out these values. Okay, great. So fixed end moments, then these fixed end moments are known. Okay, these fixed end moments are known for a given loading case. Now let's see how to determine this moment due to rotation and settlement. Okay, so next we discuss how to determine moment due to rotation and settlements. Now this is the moment due to rotation, and this is the moment moment due to rotation and settlement. Now here we have contribution from theta c, then we have contribution from delta d, and then we have contribution from this support settlement delta c and delta b. Okay, what we do next is we'll now again, since it is the linear superposition is the method of superposition is applicable here, what we can do is this moment, since it has contribution from all these the theta c, theta d and delta c, delta b, we can say that this is equal to the moment due to theta c keeping all the values 0, and then moment due to theta d keeping all other corresponding rotation and displacement 0, and keeping delta c and delta b non-zero, and for delta c and delta b keeping theta c and theta d non-zero. Okay, so in m dash cd and m dash dc we have contribution mainly from three parts. One is delta theta c, theta d, and the relative support settlement, which is delta b minus delta c. Okay, now let us see, first take the contribution from theta c. Now to get the contribution from theta c, what we have to do is we take the same beam, suppose same beam, which is now this is the deflected shape, which is which has the deflected shape is obtained by giving a rotation at c which equal to theta c. Okay, now and keeping all these other degrees of degrees of freedom or other rotation and translation 0. Okay, so if you remember again in the last class we discussed, if you take a propped cantilever beam, this is essentially a propped cantilever beam, right, subjected to some moment at the subjected to some rotation at c, and because of this rotation the moment generated at the free end, and this rotation is caused by some moment. Okay. Now if you recall in the last class we also discussed how to determine the stiffness coefficients, and for some typical idealization we computed the stiffness coefficients. Okay. Now suppose the stiffness coefficient is kcc and kdc, and what is kcc? Kcc is the moment at c due to unit rotation at c, and then kdc is equal to moment at d due to unit rotation at c. Okay. Then if we multiply that stiffness coefficient with corresponding rotation theta c, we get the moment. Okay. So then the moment at c will be the stiffness coefficient kcc multiplied by theta c, and similarly moment d will be kdc and theta c. We will see what is the value of the stiffness coefficient shortly. Now similarly this is the moment so kcc and theta c, this is the contribution of theta c towards this, and this is the contribution of theta c towards this. Now next we take contribution from theta d. So idea is we take the same beam and give a rotation at d, keeping other rotations and settlement 0. So again do the same thing. So this is cd and the moments are shown in clockwise fashion, and because of this clockwise moment this beam will deflect like this, the rotation at d will take place like this. So again so what would be the moment at c due to the rotation at d? This will be kcd into theta d. Kcd is the stiffness coefficient, which is essentially the unit moment generated at the moment generated at C due to unit rotation at D, and similarly the moment, corresponding moment at D will be kdd into theta d, and kdd is the stiffness coefficient. And what is this? This is the moment generated at D due to the unit rotation at D. Now this stiffness coefficient, when multiplied by the corresponding displacement, we get the corresponding associated force or moments. Okay. So again, this is the contribution to this because of due to theta d, and similarly this is the contribution to this due to theta d. Okay. Now we have obtained the contribution of theta c and contribution of theta d. Next we need to see what would be the contribution of the support settlement. Okay. Now suppose this beam, now when we take the contribution for support settlement, then all other degrees of freedom, means theta c and theta d have to be 0. Okay. So we allow only the segment CD we allow the deformation such that only the settlement of the joint takes place. There is no rotation of the joint is allowed. Okay. Now, so this is the settlement delta C at joint C, and corresponding, and the settlement at delta D is at D. Okay. Now suppose corresponding moment generated at C is phi CD and delta CD. Delta CD is delta D minus delta C. So it is essentially the relative settlement. Okay. Now, so what is phi CD? Phi CD is the moment generated at C due to relative settlement, due to unit relative settlement, or settlement of D with respect to C. And similarly phi dc is equal to the moment generated at D due to the unit relative settlement at D. Okay. Please note the delta C is computed, delta C is defined like this. Okay. Because if you define delta CD as delta C minus delta D, then the corresponding stiffness, sign of the stiffness coefficient term will also change. So whatever stiffness coefficient term that I am going to show you, that is consistent with this diagram. So if you are using different sign convention, and if you are defining delta CD in a different way, please make sure that you take the associated coefficients accordingly. Okay. So these are all stiffness coefficients, right? These are all stiffness coefficient. These are all stiffness coefficient. Now we will see what are the values of these stiffness coefficients. Now if you recall in the last class this is moment due to CD last class. So now before we show you what are the expression for the stiffness coefficients, then what we know is this is equal to this plus this plus this. So total the moment generated due to the entire, considering all the deformations is equal to the moment generated due to theta c plus moment generated due to theta d and moment generated due to support settlement. Okay. There is, we are not discussing anything new here. This we have been doing the same thing right from the beginning of this course, right? Now then what is the expression for these stiffness coefficient? These stiffness coefficients expressions are this, we have already done it in the last class, right? These values we already obtained in the last class. Please check, please note that if the phi CD is negative here, it is negative because this is how we defined delta CD. If we define delta CD as delta C minus delta D, then this becomes positive. Okay. Now, so this depends on the way you define delta CD. Okay. Now, so these are the stiffness coefficients, and we know how to get these stiffness coefficients, right? Great. Now, next is once we know the stiffness coefficient, then what will be okay, then what will be m dash CD? M dash CD will be say m dash CD will be what? This is the moment at C. Moment at C will be the moment at C due to theta C, moment at C due to theta D, and moment at C due to delta CD. And what would be the moment at C due to theta C? Moment at C due to theta C will be KCC into theta C, where KCC is the associated stiffness coefficient. Similarly, plus what would be the moment at C due to theta D? This is KCD into theta D. Okay, and then again plus the moment at C due to support settlement, this will be phi CD into delta CD. So this will be the total moment at C. Similarly, we can write m dash DC is equal to then moment at C due to theta C, which becomes K DC into theta C, and then plus moment due to D because of theta D, this becomes K DD into theta D, and then plus phi CD or phi DC into delta CB, right? Delta CB. So this is the contribution from this, and we also know that these KDC and KCD should be same, okay, and which is evident from this figure. You see that KCD and KDC will be same, okay. Now, if we write that in a matrix form, then what we have a matrix like this, okay, the same expression but written in a matrix form. And so this is the stiffness matrix for segment CD, okay. Now here one thing please note, this is for CD, this is for CD, and similar stiffness matrix you can have for different members. Now, when you are calculating these stiffness matrices for different members, the coefficients, for instance, the coefficient is 4 EI by L, KCC is 4 EI by L. Implicitly, it means that in this case EI of C and L of C means length of segment CD and flexural rigidity of segment CD. Now, when you go to another member, say it is AB, then corresponding coefficient will be in order to get the corresponding coefficient, you need to use flexural rigidity of that segment and length of that segment. Okay, it is not explicitly written here, but implicitly it is assumed. When you see L, L means the length of member CD. When you say EI, it means the flexural rigidity of member CD, and that may change for different segments. Okay, great. Now, next, if we substitute these values from this, then this becomes this expression. You see, this is a symmetric matrix. Okay. Now, so this is the expression for the bending moments, this m dash CD and DC for for segment CD. Okay. Now, so now we have seen how to determine the fixed end moments, and just now we have seen how to determine this. So we have this with us and we have this with us. Then this plus this is equal to this. The MCD will be, so MCD will be M dash CD plus M fixed end moment CD, and similarly MDC will be this plus this, right. So then what we have is, if we write that again in a matrix form, say MCD will be this plus this, and MDC will be this plus this. Okay. Now, let us express this. Just now we have derived the expression for this, and if we write that, and here we have MCD is equal to MCD, these are fixed end moments, plus this is the stiffness term, stiffness for that segment. okay, into corresponding rotation minus this is the contribution from the support settlement. If we for a problem, if there is no support settlement, there is no for frame problem we will see that the frame can have sway or non sway. If we find that there is no support settlement, then this part becomes 0 and only you are left with this part. But this is a very general expression where we consider all the possible degrees of freedom. Okay. Now this equation is called slope deflection equation, but to be specific, that equation is a slope deflection equation for member CD. Okay. Now if we take another segments, the similar slope deflection equation can be obtained, but in that case only difference will be, for instance, if it is for MB, so this become, instead of CD it becomes MAB, fixed end moments as MAB, fixed end moments for MBA, corresponding this become theta C become theta A theta B, and then delta CD becomes delta AB. Okay. So similar expression, similar slope deflection equation can be derived, can be obtained for all the members. Okay. Now once we have this equation, slope deflection equation, let us see how this slope deflection equation to be used. Okay. Now as I said, we can have this is the slope deflection equation for member AB, and then similarly we can have slope deflection equation for member BC, member CD, and member D. For all the members we can have the slope deflection equation for this case. Now for a given problem, in this case you have 4 segments here, but if your problems have the problems can have any number of segments, so whatever may be the number of segments, you have to apply the slope deflection equation for those segments. Okay. Now so once we have this, next is, see, this gives you the slope deflection equation for each segment separately. This is for this segment, this is for this segment, and this segment separately. Now but in actual structure these segments are not separated, these segments are connected together. When they are connected together, they have to satisfy certain conditions, compatibility and equilibrium conditions. Compatibility conditions we already considered. Okay, but now the equilibrium needs to be satisfied. And what is the equilibrium condition? Equilibrium condition says that, what is equilibrium condition? Equilibrium condition says that, see, that at point A, at point B, say this MBA is the the moment at B obtained from segment AB and moment at B obtained from segment BC, they should satisfy the equilibrium condition. Okay. And similarly for similar at C, similar at D, and similar at E. D is equal to 0 in this case because it is a roller support. So at this end D is equal to 0, that is the equilibrium condition. Now suppose at BA, instead of at B, if we have a moment like this, suppose there is no external moment at joint B, suppose at joint B you have an external moment like this, then what happens? MBA plus MBC will not be 0, these will be the corresponding moments here. The essence is whatever internal forces, the MBA, MBC, these are all internal forces, right? And equilibrium conditions say that internal forces is equal to external forces. Now since internal forces means here internal moments, that should be summation of all the internal moments should be equal to the external moment. The external moment is 0 here, that is why the summation of all the internal moments are 0. This is the equilibrium condition, right? Now then next what we do is, so next now if we solve these 4 equations, we get theta A, theta B, theta C, and theta D. Okay. Now next is suppose, so this is final approach. Okay. So this is the slope deflection, mechanism. Once we obtain these theta A, theta B, theta D, then we can use this term to get the internal forces in on these members. Now before we demonstrate that through some example, let us find out a relation between the expression that we showed in the previous, in the general discussion in displacement method and the slope deflection method. Consider consider these two member BA and member BC, and the member B is common, and then satisfy the equilibrium condition at B. What is the equilibrium condition at B? Equilibrium condition at B says that MBA plus MBC is equal to 0. So, MBA is this and MBC is this. So, this plus this should be equal to 0, right. Now, so this plus this should be equal to 0. Now, if we add them, then we get an expression like this. Okay, you can try this. So, what you have to it is written in a matrix form. Now, you have to write the MBA in an algebraic form, MBC in algebraic form, and then add them. If you add them, you will get an expression like this. Okay. Now the interesting thing is, now this is say KBA. So, K, and this is K BB, this is K BA, and this is K BC, this is KBC. If we do that, then this expression becomes KBA theta A, KBB theta B, KBC theta C, and this is phi AB and this is phi BC. Now, if we define your degrees of freedom like this, that theta B is equal to D1, theta C D2, and so on, means point B is 1, 2, 3, 4, then this expression can be rewrite, this expression can be rewrite as this. Okay. Now, what is this? What is MBA plus MBCF? If we go back, if we recall your this is the slide I showed you in the previous class. What is MBA plus MBC? This is the equivalent joint load F1, right. So, this becomes equivalent joint load F1, and KBA become K21 because the point B is now denoted as 2 and point A is 1. So, this is denoted as this, and now you see this expression is very similar to this expression. This expression where K14 is equal to 0 and there is no support settlement. Okay. So, the expression just now, this expression already we discussed while mentioning the general, giving the general overview of displacement method, and this is a particular form in slope deflection in a method which is termed as slope deflection method. Okay. Now, this is the purpose of this, to show the similarity between the final expression that we get and the discussion in the previous class. Okay, let us just summarize this. So, you get you solve this equilibrium equation to get the corresponding displacement. Once we have the corresponding displacement, this corresponding displacement can be substituted in all these segments, the slope deflection equation for all these segments, and get the member forces. Okay, the MAB MBA, get the member forces. So, this is slope deflection method. Now, probably when we demonstrate this through one example, the idea will be clear, that we will be doing in the next class. Okay, see you in the next class. Thank you.